So today I'm going to get sort of deeper into this polyfold machinery with actually try to tell you sort of a non-trivial implicit function theorem in it. Sort of review how that plays out for describing Gromov-Witten moduli spaces, and then see what in the world we're going to do with nodal curves. Same literature, the nonlinear Fredholm theory I wrote a little paper on to make life easier for everybody, I felt. And I actually worked out the description for Hamiltonian Floer theory up to a lot of technical details, but I think the basic ideas are there, even near broken trajectories. So you should not look at that though. You should look, at the Salomon lecture notes and try and figure out how to do it yourself. And when you get stuck, you can look. But first, I got a little flustered last time in trying to rewrite scale differentiability in terms of some estimates. So since that was a very precise statement, let me correct the very precise wrong statement. So I was trying to say, in terms of estimate, how when you have a map just on the infinity levels, you can see whether it's scale differentiable. And so the first one was to say, well, this is the old definition, on every level when you shift by one, you should have a differentiable map. Right, that means that you need some kind of difference quotient converging to 0, but that also certainly means that you need this linear map. And at this point, I'm not sure that you can really do that in terms of just points x that are sort of C infinity. So let me say you need that differential at every x on level fk plus 1, and that means you need to be able to start at f1. And that should be true at least on some level k equal to 0, so there should be a linear map from E0. Oh no. I'm mapping f to E, which is really bad. So f1 to E0. Linear. So, such that that's a good approximation on all kinds of levels. That, of course, already asks, this to sort of map into the right spaces. But you could think of it, well, actually, let me fudge a little. You could think of it as mapping f infinity to E infinity, which it will do in the end. And then at least this makes sense. But that was not the full definition, right? Just having this as a definition didn't give us a chain rule, so we needed something else. We needed this differential to actually, at a point in fk plus 1, be a linear map not just from fk plus 1 to ek, but from fk. So a little bit better. And that, of course, now I can write in terms of, and I want it to be a bounded operator. And that I can say in terms of an estimate. So for all k, I'd like the differential acting on vectors h divided by the norm h to be finite, I guess. Supremum for h not equal to 0. And here, right, the crucial difference is I want to map fk to ek, so I'm allowed to take the quotient by fk. Okay. So that's the switch, right? So it needs to be a quadratic approximation only from fk plus 1 to ek, but then the linear operator needs to be nice between preserved levels. So, and then, of course, once you've said this, you can then say continuously differentiable, which would mean that that map here is SC0, so continues on every level. If you manage to say that in terms of estimates, then it's going to be enough to define this differential just at points in f infinity, because then you get the rest out of the continuity of the differential. But if you don't assume that the differential is continuous, then you need to check these two conditions at every point. So you need to actually write down this differential in such a way that it makes sense. But thinking back about the reparameterization, right, there was this issue that the differential that we were guessing had sort of a derivative of our loop inside. But that made perfectly nice sense as long as that derivative was C1. Sorry, as long as that loop was C1. Ooh, except then you're not mapping to E infinity. Okay, so that was a lie. Okay, so we can't do that. Doesn't map. Right, because if I'm at a point where the function itself is only C1, that is going to get multiplied with some number and should then give me a vector in here. If x wasn't smooth, that's not going to be smooth. So. All right. Okay, so scale warm-up gymnastics. Now we're going to assume that we're somewhat fluent in scale calculus, and here was the wishful implicit function theorem that we'd like to hold in the nonlinear case now. So scale smooth map that we're going to need to say what it means for it to be Fredholm. And then if it cuts 0 transversely, we would like the 0 set to be a smooth submanifold of the right dimension. And, well, the proof is by finding local coordinates, and that uses some kind of, Newton iteration contraction mapping principle. You need some kind of contraction. And so we saw that in this sort of scale differentiability, that doesn't give us enough of a contraction property. So instead, we're going to just define Fredholmness as an operator for which this proof works. So first of all, we'd like things to be regularizing, which has something to do with making sure that the 0 set is in E infinity. Right? And in the nonlinear setting, this means that if f of E is in Fk, then E was already in Ek. And then you want some contraction property in local coordinates. So that's a little more complicated. So, and you need that near each 0. And I'm now going to take local coordinates in which E becomes 0. So my local coordinates I'm allowed to split, just like in the definition for a Fredholm operator. Right, I'm allowed to split something off that we're thinking should be the kernel of my linearized operator, and I'm splitting something off that might be the co-kernel of the linearized operator. And we would like the map of be of some form. So in the first finite dimensions, I really don't care what form that is. And then I would like this to restrict to an isomorphism between these infinite dimensional parts, the E and the F. Complement of the kernel to complement of to the image of the operator, possibly. Right? So ideally this just maps W to W. Of course it doesn't. It's a nonlinear map, so there's some error. But then I'd like that error to be a contraction, and a contraction for every V, so that this is essentially invertible. So, and that means I need it to be a contraction on every level. So let me first write down just what you need for that proof to work. So when I fix a level and an epsilon, no, for every level there is an epsilon, so that when my finite parameter V is small and I have 2 points W1 and W2 that are both small in the EK norm, then V at that fixed V is a contraction in W, meaning if I look at those 2 different points, that contracts with a number theta less than 1 in the norm scale where I actually preserve levels. So that's the estimate that we would have needed last time to finish the proof and have a contraction property to find the chart. Thing is that that's a perfectly nice definition of Fredholmness, and I think that satisfies the implicit function theorem. Unfortunately, you would then like to prove some more things about Fredholm operators. For example, you would like to know that when you add a compact operator, it stays Fredholm. Yeah, that we do that a whole lot. And in particular, we want to do that probably when we're trying to perturb our Fredholm operator. You have to have some kind of things that you add and it stays Fredholm and keeps the same index. So at the end of the day, we actually need to fix the theta ahead of time. So, and we need to allow ourselves any theta that's bigger than 0. So that means this, if I get closer and closer to 0, this gets a contraction with very, very small parameter, so something that converges very fast. That's true if this was a smooth section and it was traditionally Fredholm. You can look at the proof of this in the proof of the standard implicit function theorem, and you can see how you can get that very small. It's simply that theta sort of comes from an error as you change the base point of your differential, and so if your differential is continuous in the operator norm, that's exactly where theta goes to 0. So we need that. So that's a nice definition. For the purposes of having a theorem, it's not so nice a definition for the purposes of actually checking it. Because you'd need to actually find those coordinates, prove estimates. That doesn't look like you can sort of just quote some standard facts about the d-bar operator. So in the Gromov-Witten paper, where Hofer, Wysotsky, Zehnder prove their first instance of an operator being Fredholm, they actually use, they prove a lot of intermediate steps, and well, I wasn't actually looking at that, but I was trying to answer the question, and people kept asking me, like, how in the world do you actually ever check this? So I tried to axiomatize what you do, and this is essentially a sort of subtle difference between the Gromov-Witten paper and this. But of course, I like this version better. So essentially, in order to, well, regularizing, we know how to check that. That's elliptic regularity. So we need to understand how to get contraction. And the statement is that you get contraction from linearized Fredholm and a little bit of differentiability. So you need good differentiability only, well, you need a lot of differentiability, sorry, but you can lose it in finite dimensions. So this is very similar to the Siebert approach, where he says, well, in finite dimensions, there's some extra finite dimensions in which I don't need to care about differentiability. And that's the same effect here. So reason essentially is that you need C1 estimates really in order to get this contraction. But if you have some dimensions in which you don't have C1, you can chuck them all into this finite dimensional extra piece. And in those, you're going to need some continuous properties, but not directly the contraction. And so that might not be the kernel, right? So you might throw more dimensions into this finite dimensions just because you don't have enough differentiability there. And you just pay the price on getting more dimensions into this until you have an isomorphism again. So at the end of the day, this really is not the splitting off of kernel and co-kernel, but you're adding stuff that comes from lack of differentiability. But truth be told, the notion of uniformly here is a little complicated, and so I just thought I should write that down. Also because things get really nice when we look at the Cauchy-Riemann operator later on. So C1 up to finitely many dimensions means I'm able to split my Banach space into something finite dimensional and some extra scale Banach space. And so really my map comes as a family of scale smooth maps. F sub R of E. And then that's supposed to have a whole number of properties. So first of all, right, it's supposed to actually be C1 in the dimensions that are not these D dimensions. So for any level R and small r, I'd like this map FR to actually be a C1 map on that level. So classically C1. And then I'd like that to somehow be uniform. So that means the continuity of the differential that I have from the first assumption, so right, dfr now at every point E twiddle k gives me a bounded operator from E twiddle k to fk. So that's continuous in those directions. It's not necessarily uniformly continuous because that's an infinite dimensional space. Right. But it's always, well, it's near a point, of course, it's uniformly continuous, because that's the definition of continuous. And I'd like that estimate to also be uniform in R. So. There's some difference between the operators at two different points in here, or a point in here and 0, and I'd like that to be, oh god. So there's a reason I didn't write this out in formulas. I think, sorry, I want 2 points R1, E1 and R2, E2 near 0, and the difference between these operators should, in here should be small, no matter which point I have there. So that's the first meaning of uniform. And then I also need some sort of uniformity of the kernel. So this is something to do with, oh goodness, probably lied in the, well, let me write this out and then see what the difference is between this assumption and the previous one. So if I have a sequence of parameters going to 0, so what we're thinking here is that these are really gluing parameters and we're going towards a node here. And I have a sequence of vectors of length 1, so these are in each whittle, that, well, go towards the kernel. So the derivatives at point 0 in E of the Ri map on this are supposed to go to 0. I would like to compare that with the kernel of the linearized operator at the sort of nodal curve, so when R is 0. And I can apply this to the same vectors EI. So when this goes to 0, I'd like that to go to 0. Right. So that would follow from the previous line if the uniformity of, if the operator norms, if the map from to these operators was uniformly continuous also in R. Right? But I'm not asking for this. I'm just asking for the estimates for the continuous dependency on E to be uniform in R. So I'm not asking this to converge, so I'm not asking this operator here to continuously depend on R. There's just some uniformity of estimates with respect to R, so some uniform continuity. The only thing that I ask, for varying R is, I'm not even asking for an estimate between these two operators. I'm just asking that if you're going to the kernel here, you're also going to the kernel there. So, and that ends up being exactly what one can prove for the Cauchy-Riemann operator in gluing situations. Nice thing is, these are estimates. And right, that's this. So that's all the meaning of uniformly C1. And then I should say what I mean by uniformly linearized Fredholm. So, first of all, each one of these should be Fredholm. So if I linearize get an SC operator between E twiddle and F, and I'd like that to be a scale-Fredholm operator. Right? For small enough R. That's something we looked at last time, but essentially meant, well, you needed sort of linear regularizing, and you wanted to be Fredholm on the first level. And then Fredholmness on the other levels kind of followed. So that's what I mean by the linearized operator being Fredholm. And I don't need this at points other than 0 because of this continuity here, right? So if I now linearize at an E that's close to 0, then this continuity here is going to tell me that I'm still Fredholm. However, I don't have continuity when I vary R, so that's why I need to apply this, ask for this for all small r, and I'd like at least the Fredholm index to be independent of R. So you're going to ask, well, how is that ever going to give me some information on how kernels or co-kernels relate? Well, that's where this second line comes in. That gives you sort of an inclusion of kernels. And then I think some other thing gives you an inclusion the other way of co-kernels. And so then asking the index to be constant actually kind of identifies kernels and co-kernels in the limit. Total like minimization of things that need to get checked. But well, so I hope this looks a little more reasonable to check. Yeah, once given an operator, it's a longer list, but you don't need to. These are things that you can check. These are not things where you need to have a good idea for what your local coordinates should be. Well, you need to have one idea, namely what to split off here. So that's and well, so obviously we should this should work for the d-bar operator in the local charts that we already have for Gromov-Witten modular spaces, and it's going to work in a very excitingly boring way, where not much is going to happen. So here's the claim again. We can cut out Gromov-Witten moduli spaces by polyfold Fredholm section. Now at least I've told you what I mean by Fredholm. And we ought to do that on object level. We did, well, that's actually lecture 2. We did the description, and then I revisited in last lecture. So the lecture 2 description was just looking at H3 maps that are near there and satisfy these hypersurface conditions. And the lecture 21 extra thing was to just add scale in front of everything. And so here, right, same setup, 0 set modulo stabilizer is an open subset in my moduli space. And now the question is, what do I mean by Fredholm here? So my d-bar operator, I'd like to be Fredholm in the way that I, well, not defined it, but that maybe fits into the axioms of my lemma. So that's where, if we're anal, we have to actually not write this space down with sort of H3 plus K filtration. We have to actually write the Banach space, or the linear space, down. So that's the sections of the pullback bundle that satisfy a sort of linearized hypersurface condition. And then a section here corresponds to X U of Xi, where U is somehow the center of my chart. And so, in that chart for this Banach, scale Banach manifold, the d-bar operator becomes this map. And takes values in 0, 1 forms of the appropriate regularity 1 less. So that is now a nonlinear map between scale-Fredholm spaces, sorry, scale-Banach spaces, well, scale-Hilbert spaces really. And so I can try and ask myself whether it satisfies the conditions of being scale-Fredholm. So first condition is regularizing. Right? So if I call this, let me call this here U sub psi for the moment, then let's see, what do we know? Right, so we know from elliptic regularity that if d bar U sub psi is in, let's see, fk, so fk is age k plus 2. That means that U itself should already be in H 3 plus K. Oops. And now U in local coordinates is about U plus Xi. And so I would like to deduce that really Xi is H3 plus K. Well, in order to, that means my sort of center of the chart U better be smooth. So essentially, you don't want to use these charts with the exponential map at maps that are not smooth. And that's perfectly fine because really we only need to center our charts at actual holomorphic curves, and we know that those are smooth. So. So there's various reasons why you would center your chart at smooth curves. It's just good to see that not everything is tautological here, right? There's sort of a little bit of sort of technical difficulties cropping up, like this one here, but you can solve them by, centering at good points. Good, so that's regularizing it. Now you could try and prove the contraction property by hand. Right? Or you can make your life easier and quote my lemma. And in this case, well, there's nothing that looks non-differentiable. There's no shift map going on. Right? So we might as well take EK itself. So that means there's no dimension that I split off, so I can completely forget about R. I just have this one map here. C goes to d bar of UC. And I want that to be, first of all, classically C1 on every level. That's exactly what we know from back in the days when we said, in the Banach manifold setup, this actually is a smooth section. Right? And it doesn't matter on which level I am. It's always, well. And here we just need C1. So this is something we believe or have claimed before. Similarly, now the continuity, well, I just need that to be uniform in E near 0, and I'm now confused. I think that should actually follow from being C1.
Should be tautological.
Right.
When there's no R involved.
Right. When no R is indeed. Right. Certainly this here is completely tautological. Right. So there's no difference between these. So that's like. And finally, we need our linearized operator, but that's just our linearized d bar operator. And I'd like that to be scale-Fredholm, no R dependence. So that's the opportunity to review scale-Fredholmness. So life is actually even simpler. We don't need Fredholm property on all levels, right? We just need the d bar operator from the 0 level, so hk plus 3 to hk plus 2. Oh, sorry. 0 level means k equal to 0, right? So we just need to convince ourselves that as a map from h3 to h2, that's SC0. Probably believe that, oh, geez, sorry. That's, we just need that to be Fredholm, right? Of course we need it to be SC0 and regularizing. That means that something is on all levels. So, first of all, du d bar j maps all the EKs to the FKs continuously, and it sort of has a pseudo inverse in terms of regularity. So if take sort of the pre-image as a point set of FK that sits in EK. But that's, exactly knowing that, elliptic operators are well behaved on all scales of Sobolev spaces, and, elliptic regularity for the linearized operator also holds on all scales. So this is all over again. So things essentially boil down to, the definition of, when you have more differentiability than scale structures, allow you, really all you need is nonlinear elliptic regularity together with linear elliptic regularity, and then sort of the linearized Fredholm property, right, on the zeros level. So. And then the extra differentiability gets you the contraction property. So, of course, this is going to get a little bit more exciting when we're at nodal curves. So then we actually will have parameters R. So, right. So, this means now we have convinced ourselves that not only do we have a decent enough bundle, our section also is Fredholm locally. And so, recap and also correction of chaos that I produced last time. Right? So once you have all these local descriptions, well, near smooth curves we're good. Near nodal curves, that's what we're going to need to do, so that we can actually cover our whole moduli space. But say we have that, then we need to look at the morphisms. And they'd better, well, first of all, intertwine the Fredholm sections, and also actually have scale-smooth structure maps. So the way that I identified the morphism space as a scale Banach manifold was a little fuzzy because I had forgotten to think about isotropy. So after thinking about isotropy, what's going on here? Right, so I want to look at pairs V and reparameterization so that the phi takes V into the different slice U prime, which, so U we're thinking has something to do with slicing condition 8, and U prime has something to do with slicing conditions H prime. So the claim was that locally this looks like U times just the stabilizer in the chart for U. And the way that that goes is what you actually want to do is, well, I'm making some simplifying assumptions here. Namely, I'm making the assumption that the center of the chart U actually also can get reparametrized into U prime. Otherwise, I have to change the center first. So I'm assuming that I can actually reparameterize U with the phi 0 into U prime. Which means, right, if I look where U intersects the H primes, well, that's going to be a whole bunch of points, and after applying phi 0, they contain 0, 1, and infinity. So phi 0 of Z needs to be in here for my 3 marked points. And so once I have that, I can define my map when V is approximately equal to U, and G is something that fixes U. So in particular, that means not only is U composed with, phi 0 takes U to U prime, but also G composed with phi 0 takes U to U prime, because it doesn't do anything here. And so the idea is to now take the reparametrization that's close to this one here. So to find that, I need to, so phi is going to be approximately equal to G composed with phi 0, and I can determine it by looking at those points. Namely, I look at the pre-images of H prime, but now within the, within the neighborhood of phi 0 of Z if G was 1, but if G is not 1, I'm supposed to move those neighborhoods around. So if U was a multiple cover, it's going to hit every one of these surfaces a couple of times. And I could have like little disks around the places where U hits those, and then G permutes those disks. And so this G here picks out on which disk I'm reading off my intersection point. And that intersection point is then supposed to be phi of Z. So that at least now is a definition that depends on both V and G and gives us something that's actually reparametrizes to the right space. So reason I want this very much in formulas is that I wanted to argue that all my structure maps are scale smooth. Right? And there I had this decomposition in particular of this structure map. That's the target, right? So, and that composition now has a precise formula here. That's what I did just before. So, let's see, with that precise formula, right, I still need to, so first I need to ask myself, well, reading off where I'm intersecting these hypersurfaces, how differentiable is that? And not, I also somehow said the wrong thing here. So if V is in CL, going to, well, of course they all need to be somehow transverse to those hypersurfaces, but reading this off in P1 will be, that map will be as differentiable as V is. So this is a CL map. And now the good thing is that H2 plus L is in here. And so I get CL maps on level L minus 1 on the target. And that sounds a lot better than scale scale differentiability. So, right. Well, we haven't formulated out scale smooth totally, but I mean the shift here is a really nice one, right? So this here is E L minus 1. So I get a whole lot of differentiability, right? Scale SC1 would just ask to go from E L plus 1 down to whatever target space to ends BCL. So I have a bunch more space here. So, and that gives me the full scale smoothness of that. And then this map here is non-trivial really only as a map from the 3 points of the sphere to the Möbius group by solving that these points are equal to phi of z. So the bigger concern here is whether that's a well-defined map, but it is when these points are all non-equal, right? When they don't coincide. So I should probably take out the diagonal here, and then that's perfectly smooth. And then the last part is where the reparametrization happens, and that really is why we define scale differentiability as we did, so we have scale smoothness. So, and then my chain rule really tells me that the whole thing is scale smooth. All right. So that was that correction, right? So this means that morphisms make sense by themselves and give this, bundle a good, smooth structure in some sense. Now, what does that have to do with the actual section? So I want functoriality of my section, right, which is somehow the d bar operators in all my charts. So before I can really talk about functoriality of that section, I actually need to tell you what the morphisms of the bundle are. I didn't really tell you what the, I did say at some point, I think, what the bundle is. Right, yeah, because that's the 0-1 forms. But, right, so the morphisms already had a slightly complicated structure, right, because these objects we're thinking of as the linear spaces here. So this here I want to identify really with u sub xi, it's the x u of xi, and that goes to, well, so the morphisms identify xi with xi prime, so that u xi prime is u xi composed with phi. So on the morphism level you reparameterize, and well, what should be happening in the fiber? Well, let's see what the d bar operator does with reparameterization. Well, this is just the 0-1 part of the differential, so we should take the differential of u composed with phi, and then take the 0-1 part, and because phi is complex linear, the 0-1 part just hits this guy here. So d bar operators just get reparameterized with the differential. So that means when I have now sort of an object here, which is really a pair xi, comma eta. Let me just write the thing in the fiber. Morphisms here intertwine eta and eta d phi. And then I can say what xi does, what sigma does, right? So sigma takes xi to whatever eta that is, d bar u xi. And here I also have the d bar operator, but on u xi prime. But this identity for the d bar operator exactly tells me that these squares commute. And that's what functoriality means. That, yeah, the section is compatible with the morphisms. Hooray. And that really is, well, yeah, we need, well, you could have thought of taking different morphisms, right, that are sort of nicer differentiable, but, you know, the d bar operator forces you to take, you know, morphisms that, you know, are at least related by this fundamental equation. So, there's sort of a lot of places where you think maybe I could fudge something ingeniously here or there. You know, there's always some place where you get back to the fact that you do want to count holomorphic curves and nothing else. And so that really often forces you to write down just one theory. Good. So, all right, we have a Fredholm functor, in fact, not just a Fredholm section. So, but all of this is sort of meaningless gymnastics if we can't start and actually doing something meaningful near nodal curves also. So, same theorem, except now we're really going to look at the part that's in the Gromov compactification and not in this sort of nice smooth part. So, right, and that's where local Fredholm description is really going to become a little more non-traditional, right? I mean, the way I just maybe sort of convinced you that there was one before was to just, you know, go into this sort of finite dimensional gluing, right? So we stabilized both problems and then just did gluing in finite dimensions, and in finite dimensions everything is Fredholm. So we got a local Fredholm description, but it was in finite dimensions. So now we'd like to just, you know, not solve at all any time and just get the Fredholm description straight on near the nodal curves in infinite dimensions. So let's see. And right, so suppose, well, this is the simplest case as usual, right? We'd like to just look at a curve with one node that's described by two maps from spheres with, you know, matching marked points. And, well, yeah, we always draw these as spheres, right? So, but note that, yeah, there's no reason why the image of u minus might not intersect the image of u plus in some bad way. The only redeeming thing we know is that these two marked points here go to the same point. And then we know a little bit of unique continuation, so they can't actually coincide for a whole while and then, yeah, go apart. But they can certainly intersect transversely. And in fact, that depending on whatever dimension you're in, that intersection also is forced to be transverse. certainly, right, the way we always draw this as tangent is really wrong. Right? Because once things are really tangent to infinite order, they're the same. So it's just the only good way to draw a node in 2 dimensions. So, right. Very naively, right, our goal is to write a neighborhood of this point in my moduli space as the 0 set of some kind of section. So really, this whole configuration is just one point in M bar, right? And M bar itself is some fuzzy thing in which that point lies. So we'd like to embed that into some nicer space. So what we need to do is start with, well, let me look at least the smooth elements in my base. So, well, near the nodal curve, there's certainly going to be non-nodal curves. So those will come from smooth maps on P1 modulo Möbius reparameterizations. But certainly I can also change my nodal map within the nodal maps. So those will be, oops, we've reverted to punctured drawing. No, okay. Right, sorry, P1 to M, of course, right? And so I need pairs of maps, but I'm going to need to keep my 2 marked points fixed so that I can make a fiber product. So, one at minus infinity, one evaluation at 0, and they should, map to the diagonal. Get to the same point in M. So I have a little bit of a different group here. P1 fixing infinity and P1 fixing 0. So that's just the curves with one node, and then of course you could take more complicated bubble trees. And Gromov convergence was convergence in a topology on this space, which was given by pregluing. So, that makes sense that we should put that pregluing topology on that space also. So at least if we're now saying that the 0 set is the holomorphic ones in here, then at least our Fredholm section is proper in the sense that its 0 set is compact. Because that's when we have the pregluing topology, that's the statement of Gromov compactness, that on this space, this, holomorphic ones are compact with respect to the pregluing topology. But this is, well, let me point out the perversities, right? So there's, points in this that come from one map, there's points in this that come from 2 maps, there's points in this that come from 25 maps. Also, the group that I'm quotienting out by changes, right? This is one Möbius group of dimension 6. Here, I'm sort of quotienting, well, there's a fiber product going on, which is not good news anyways, because if you want that to have a smooth structure, you'd better have that fiber product transverse. But beyond that, really, I have a product of 2 Möbius groups of dimension 4 each. So the group that I get here is dimension 8. Or even more if I allow this marked point at which I have the fiber product to run. Certainly the dimension of the group that I'm quotienting out by goes up the more nodes I have. So it's not even somehow a situation like the one before where we had sort of a nice scale smooth structure on a space of maps, and then we quotient by something that's scale smooth. It's really sort of different groups acting on different parts of the space, and you can only glue stuff together after you've quotiented out. So now the question is whether the next thing is more or less bad news. So my section, right, on this here is just d bar. Up to reparameterizations. And on this, it very much just acts on the pairs. So you could say that that's bad news because it looks even more different in each stratum. But I actually think this is good news, because that means that this weirdness in the base is reflected by the same kind of weirdness in the fiber. So if your base had 25 components, your fiber needs to have 25 components as well. And having base and fiber coupled is always a good thing if you want to think about Fredholm theory. And so not only does somehow the dimension jumps, there's sort of one copy of infinity and you have two copies of infinity. You have the same sort of jumps or effects of taking several copies of spaces in the fiber. And your section kind of mirrors that whole structure. It just sort of works on the different copies. And it always comes from the d-bar operator, which we kind of like. So it's not that hopeless. The problem is, we need some notion of smooth structure, on base and fibers now, so that this section here is Fredholm and scale smooth. So that's the mantra of what we need. And the idea is to simply write down what we have, namely pregluing, and declare that to be the definition of smooth structure. So, namely a chart. So, the generalized notion of Banach manifold will then be M-polyfold. And we need to make it so that pregluing is a chart map, because then, the description of a neighborhood of this by pregluing is going to be our chart map, which is going to give this, the structure of an M-polyfold. So let's see how we can pull that off. So let me try to copy this guy here. So that's just the data that I need to describe the nearby nodal maps. So trying to define or trying to describe a neighborhood of a broken curve. Certainly I need to have the nearby broken curves, and then I have a gluing parameter, which, is just going to be the unit, a small disk, I guess, in C. Right, where there's some gluing length and some rotation parameter. That makes up for the argument. So, right, what was my pregluing map? for the moment, let me write pairs V minus and V plus, remembering that they actually also have to satisfy this matching condition. So there's going to be a situation where I don't glue. Right, that's at a equal to 0, that's sort of gluing parameter infinity. And as long as a is non-zero, I read off the length from each of the exponential on the modulus, and I have a rotation parameter, so I can pre-glue these two guys. And then I ought to take the parameterizations out very roughly. So that, by definition, is locally surjective. So I'm just going to take my neighborhood U infinity so that it's just the image of that. So it's surjective. However, it is very much not injective. Right. Which is a pretty weird property for a chart map. Chart maps are usually local homeomorphisms. So at least they're bijections. This guy is not even injective. It has massive amounts of kernel. So to understand roughly what the kernel is, let me try to draw this map here. So it's going to be, let's see, V plus, right, so V plus has a node at 0, so I'm going to take essentially the map V plus on most of the sphere, and somewhere in a small ball around 0, I'm going to take the map that maps Z to V minus of A times Z? Z divided by A? Jeez. A is going to be very small, and Z here is going to be very small, right? So I should probably take Z divided by A. Right, so that sees, right, I took out just a small neighborhood of Z equal to 0, and I put in, values of V minus that come from a much larger neighborhood, in the sphere. Right. Yet, there's some domain in the middle here where I have to interpolate them, right? So somewhere here, where approximately equal to V plus at 0, which is V minus at infinity, right? And so I've forgotten some data, right? Namely, I've forgotten the value of V plus everywhere on this, on this part of the domain, right? So this is sort of kernel, or V plus kernel. Data of V plus that I completely forget in this pregluing. And there's an analogous image for V minus where you see that I completely forget the data near infinity. So it is sort of an organized amount of data that I forget. Right? I sort of have an idea of what it is that I forget. And this notion of organizing or keeping track of what I forget is in this following idea. So this is a pretty big space. The good news about this space is that has sort of a smooth structure, well, up to this fiber product. But I can give this a scale smooth structure. That's a nice space. And then there's a not so nice map that in general is described as retraction. So something that maps this space to itself and keeps its image fixed. So maps everything to some subset, which is not going to be an open subset at all, some weird subset, which is made exactly so that the map up here, so if I call this my pregluing map, if I restrict pregluing to this image, I would like that to be a bijection. So what's going on is there's some kind of smooth structure here, and this map is going to be smooth, or scale smooth. And the bijectivity sort of sits within a smaller subset. So that is, of course, pretty obscure. So. Right. But so it's the beginning of sort of making a little more sense of this ambient space situation, right? So what is this one point here within the whole, fuzz? Well, it's the gluing parameter 0 within the whole fuzz, and then in order to, cut out the non-transverse thing, of course, I need a whole lot of more space. I need some kind of scale Banach space here. And in this case, that's this fiber product of maps with parameterization here is going to be my scale Banach space of local homeomorphic to that. So here I have two choices, right? I can either put this fiber product into the operator so that this is just a product, or I can try and encode it, as linearized conditions on the tangent space. And so my pregluing here is some map to what I would like to become an M-polyfold. And the abstract theory says that, there's a surjection that's scale smooth to some weird space, which is going to become K superscript pi, and a bijection of this map. And let's see, right, this is also, it doesn't make sense for this to call this scale smooth because, right, we're trying to give this an M-polyfold structure, so a priori this is just kind of a topological space. But in the part where it is, the topological space that comes from maps, right, it's going to be scale smooth, and that is going to be reflected in the transition map to other charts being scale smooth. So this wants to be the chart map, which means, in a reasonable Banach manifold, it's smooth and bijective, and in a polyfold, it's factored through two maps, where one of each has that, has just one of the good properties. And so the form that this has in the applications that we know that come from pregluing is that really there's a projection that depends on the gluing parameter. And we can actually make that projection a linear operator. So this is going to be is the union over all A image of a projection times A. So it's like a fiber product over the gluing parameters where pi sub A. So pi A is going to be a family of SC infinity projections. So linear. Right, V is usually the gluing parameter in Hofer, so V is equal to A here. And so then this, you think of this as sort of a fibration where the dimension of the fiber can jump drastically. So the thinking here is that the image should sort of be the complement to the kernel. Though it's not, that's not a linear operator, but maybe complement to the ambiguity. And what that means, right? At a equal to 0, there's absolutely no ambiguity. Well, if these were in the local slice, then this image knows exactly where that came from. So there's no kernel for a equal to 0. So the image ought to be the entire space, which is, well, roughly speaking, some kind of maps on P1 times maps on P1, together with some kind of finite dimensional, matching conditions. At a not 0, the image needs to be approximately, the data that we need to describe the image of the pregluing, right? Namely, we only need to know our maps on the complement of balls around the nodal points, right? So that needs to sort of, or my fiber needs to be isomorphic to this kind of space, which is at best a linear subspace in E that's infinite codimension and infinite dimension. But that's sort of the, we've introduced a whole lot of nice structure, and we've moved the problem now into making a family of projections on a scale Banach space that has this kind of behavior. Note that one thing that happens here is, there's two different notions of scale smoothness, possibly. I could ask for my family to be, scale smooth as a family of scale operators. That is never going to give me the right kind of jumping conditions, because continuity of operators means that kernel and co-kernel stay the same in small, or index stays constant, right? So this will not allow, doesn't allow for jumping. This doesn't allow jumping in the image or kernel. But we can ask for scale smoothness pointwise. So the point is that this projection really only needs to be scale smooth as a pointwise map. So this being scale smooth, we'll see examples where that allows for pretty drastic jumps in dimensions. And since really there's no, in the global picture somehow the gluing parameters don't need to be much different from the map parameters, there's no reason why we should ask for this continuity as operators. So that's the idea. This will be scale smooth really as a map from this product, and then we're going to have this sort of whacked out subset but on that, you have a good map. So now you should, of course, all be up in arms and say, well, if you're just defining the map on this sort of weird subspace, how are you ever going to talk about the linearization and Fredholm properties? And if your spaces here change, of course, your tangent spaces are going to change, and so how are you ever going to talk about, index being constant? I'm going to do that on Wednesday. And again, this is sort of the core idea, and now you just have to make the definition of Fredholm so that on the one hand it's true for the Cauchy-Riemann operator, and on the other hand it actually implies an implicit function theorem. So we're close.